Hi and welcome to this video on using the laws of indices. So in this video we're going to cover the laws of indices. The first thing we're going to do is we're going to work back through the 9 laws of indices. These laws are given on page 21 of your formula and tables book. After that we're going to cover some examples of using the laws of indices and solving some basic index equations. So this video should be revised along with the videos which are on the laws of thirds, laws of logs, and there's also a more in-depth laws of indices video which focuses on index equation and more complex examples of those. So I'm going to link all 3 videos there in the description box below. So here on page 21, we're going to be focusing on this first column here. And these are all the laws of indices that you've seen at junior cert and we're going to use as we move into leaving cert. So the good news is there's no new laws that have been added in. The work that we're going to do is slightly more challenging than what you would have seen at junior cert, but it will stay relatively the same. So for the indices work, knowing that there's nothing really new coming along means you can really focus on revising this topic. So before we start looking at the laws of indices, it's just some terminology that it's important that you know. So indices is the plural for index. So it is the more mathematical term for power. So you're probably more used to hearing power as you work through primary school, but we do use indices as the name of this topic. And it's just not to forget the connection between indices and index. So there's 3 things that we can call that power. We have power, index, or exponent. The reason I touch on exponent, although it's more an American term, because we're going to be using a version of that word as we move into patterns and functions. So it's important to hear it here as another version of power or index. So the big number then is called the base. So let's take an example of 2 to the power of 4. 2 is the base, that's the big number, and 4 is the power or the index or the exponent. Do you get in the habit of saying 2 to the power of 4? Often students go 2, 4 or 2 times 4 when it's not. They're very different things. So do get into the habit of saying 2 to the power of 4. So the base, that big number, as we work through our laws, I'm going to talk about that if there is 1 base or 2 base and so on. And as we get into index equations, we're going to talk about it a bit more as well. As you move into the higher level course, you also work with something called logs, and that's also going to work with the base. So it's important you know where it is. So 2 to the power of 4, what that actually means is 2 by itself 4 times. So 2 by 2 by 2 by 2. So you will get 16 if you multiply 2 by 2 by 2 by 2. 2 to the power of 4 can also be put in directly into your calculator. 2 squared and 2 cubed both have buttons on your calculator. However, if you want to go on any power higher than that, on the Casio, there is an X to any power. So it is an X with a little white blank power box there where any number can be filled in. And that's the one we're going to focus on as we're working through here. So let's go through the laws now one by one. We're going to work through how they're derived or in an example, and this is trying to help you to have a better understanding of the laws. If you're absolutely fine with the laws and you'd like to go straight to the examples, just skip through the video until you find the examples. So law 1, a to the power of p multiplied by a to the power of q is equal to a to the power of p plus q. So some things to note here. Although it's not written, the fact that these two terms are written side by side, there is an implied multiplication here. Okay, so when we are multiplying 2 numbers that are the same and they have powers, we can simply add the powers. So that big number there is called our base, and the top is called our power or our index or our exponent. So I'm going to stick to probably using power as we work through. But notice that here we have two base numbers. So if we were to do an example, let's look at a to the power of 3 multiplied by a to the power of 5. So we would say that that is simply a to the power of 8. But where does that law come from? So if we break this down, a to the power of 3 is the same as a by a by a. A to the power of 5 is a by a by a by a by a. So looking at that, there are 8 a's in total, so that would be simply a to the power of 8. So you can see where that addition of the power is coming from. So now let's take a look at law 2. So law 2 is about division. Just as a reminder, anything that's written as a fraction, that can also be rewritten as division. We're going to focus on it as division just for a minute, and then we'll go back to using the fraction notation. So a to the power of p divided by a to the power of q is equal to a to the power of p minus q. So we're subtracting the powers. Again, notice that we have two a's or two base numbers on that left hand side. So let's take the example of a to the power of 5 divided by a to the power of 3. Showing that expanded, that is a by a by a by a by a divided by a by a by a. Now, it is much easier to see our division if we leave it in fractional form. So let's put this in fractional form, and we see this. What happens here, because everything is broken down into its factors, we can simply start cancelling. So that a cancels with that a cancels with that, and that a cancels with that, leaving us simply with a to the power of 2, or a squared. And if we had gone and used that law 2, we would have been able to simply subtract the powers, which were 5 and 3, which would have straight away given us here a to the power of 2. So these laws, they make our lives a lot easier. They are quite efficient to work with. You can work out the long way like this, but realistically, as you move into higher level, that's not going to be practical. So let's take a look at law 3. Here we have a to the power of p to the power of q. Now it's really important to notice here that there is only one base. Students tend to get law 1 and law 3 confused, and the biggest difference between law 1 and law 3 is that in law 1 we have two base numbers, while in law 3 we simply have one. We just have this a. So it's a to a power to a power. So the rule here is a to the power of p to the power of q is equal to a to the power of pq. Remember, pq is actually p multiplied by q. So let's take an example. Let's have a to the power of 3 to the power of 4. Using law 3, this would simply give me a to the power of 3 times 4, which is a to the power of 12. But where does that come from? So a to the power of 3 to the power of 4 is a to the power of 3 multiplied by itself 4 times. So hopefully we can see that demonstrated here. A to the power of 3, which is a by a by a, and that is written out 4 times. So if you count how many a's we have there, we have 12. So this simplifies down a to the power of 12. So now let's take a look at law 4. Law 4 is one that students really struggle with, and this is a great one that if you can recognize without having to go to calculators or the log tables, make your life very easy as we move through the questions. So a to the power of 0 equals 1. So this seems very counterintuitive for a lot of students. Basically, any non-zero number to the power of 0 will equal 1. Now you can test that on your calculator, put in any non-zero number, put it to the power of 0, and you will get 1. But why? Why is that the case? So we're going to use what we've already looked at in our laws of indices to figure out why this works. So let's take an example of a to the power of 5 divided by a to the power of 5. So if I was to work this through, I've a by a by a by a by a divided by a by a by a by a by a, and that simply gives me 1. Now, you would say straight away at that top, well, any number divided by itself equals 1. So we're all happy that a to the power of 5 divided by a to the power of 5 equals 1. No argument. However, let's think about this in terms of the laws of indices. If I was to use law 2 to do that, a to the power of 5 divided by a to the power of 5, I will get a to the power of 0. So just remember, law 2 was a to the power of p divided by a to the power of q is equal to a to the power of p minus q. So to divide, we would subtract our powers. So what we're seeing here is by using what we already know about division, so any number divided by itself is 1, and then by using our laws of indices, and specifically law 2, we get a to the power of 0, we can then conclude, so therefore a to the power of 0 equals 1. So we've worked that both ways. So what I would say as a way to try and remember this is that a to the power of 0 is basically the answer for any number divided by itself. And that is why we get it equal to 1. So if you had 3 to the power of 0, basically you had 3 to some power divided by itself, which gave us 1. Now let's take a look at Law 5. Law 5 is another very important law that tends to come up from time to time and students tend to find very difficult to work with. There are some laws here that you're going to probably know and be able to use without going back to your log tables, but it's always advisable to have your log tables open in front of you when you're doing any kind of work with indices. So law 5 states a to the power of minus p is equal to 1 over a to the power of p. Okay, so let's work through this, and we're going to use the laws that we've already looked at to help us prove that. So let's take 1 over a to the power of 5. So instead of working the way that they've given it here, I'm going to work this way here to prove it. And it is important at this point to note that all of our laws of indices work both ways. So they work from left to right and also from right to left. So we're starting with 1 over a to the power of 5. So using law 4, which we've just looked at, I can write that 1 at the top as a to the power of 0, because if you remember, any non-zero number to the power of 0 is equal to 1. I can now, because I have a to the power of 0 divided by a to the power of 5, I can now use law 2. And using law 2, which talks about division being the same as subtraction of the powers, I get a to the power of minus 5. So we can see that this line here, 1 over a to the power of 5, gave us a to the power of minus 5. One way to look at this is to think of this as going from underneath the line to above the line, and that makes the power change a sign. So a lot of people think of this as the power becomes negative. Just be careful with that, because we could work with a negative power under the line that becomes positive as we bring it up, and so on. So let's take a look at law 6. Now, law 6 and 7 we're going to approach a little bit differently. It's not as easy for us to work through it the way we've worked through the first 5 laws, but what I'm going to do instead is I'm going to demonstrate an example which will help us to see how this would work. So consider using law 1 on the following. So I have 64 to the power of a third, 64 to the power of a third, and 64 to the power of a third. So using law 1, it tells me if I'm multiplying and all the numbers have the same base, so the same big number, I simply add the powers. So I get 64 to the power of a third plus a third plus a third. So if I add a third plus a third plus a third, that will give me 1. So I get that as 64 to the power of 1. And we never write a power 1, we simply write 64. So we would have an implied power of 1 on any number that we write. So it's very hard for us to understand what a power of a third actually means. But let's take a look at the second part of this example. So let's say we had the cubed root of 64 multiplied by the cubed root of 64 multiplied by the cubed root of 64. This would simply give us 64 as well. Remember that the cubed root of 64 asks what number multiplied by itself and multiplied by itself again will give me 64. So if you go to your calculator, so on Casio, it is above the square root. You have to press shift and the square root button will get you the cubed root. And if you do the cubed root of 64, you get 4. So 4 by 4 by 4 will give you 64. So notice how similar these two pieces are. So 64 to the power of a third multiplied by itself and then multiplied by itself again gave us the exact same answer as the cubed root of 64 multiplied by itself and multiplied by itself again. So what we can conclude from this is that 64 to the power of a third is the same as the cubed root of 64. So when we see any powers which are in fractional form, they're going to link us back to the roots in some way. The important ones to note would be a to the power of a half is the square root, a to the power of a third is the cubed root, and a to the power of a quarter is the fourth root, and so on and so forth. Just take time to note, in particular this one here, a to the power of a half, because we never write the 2 in a square root. It's similar to the reason we don't write a 1 in our power, or if I have an x, I simply write x instead of 1x. It's more of a time-saving thing. So notice that if I simply have a square root, that 2, we don't have it there, so that doesn't really appear. It is just the root itself. So if you have power of a half, it is square root. And we could do the same thing as we've done here with that 64. We could do it as power of a half and show that 2, so 64 to the power of a half, multiplied by 64 to the power of a half, would simply give me 64. So we could work that through in a similar way. So now let's take a look at Law 7. So Law 7 states a to the power of p over q is equal to the qth root of a to the power of p, or can be written as the qth root of a all to the power of p. So in this case, the order in which you do the power and the root won't make any difference, and that is because both of them are part of indices, so it doesn't matter which one is worked first. So Law 7 extends Law 6, which was 1 over q. So when we talked about the power in Law 6, the numerator was 1. We're now expanding to have a numerator that is not 1. So let's consider a to the power of 8 over 3. So if I take 8 over 3, that is the same as 8 by a third or a third by 8. We can do this because multiplication is commutative, which means that it doesn't matter which order that we do it in. And we're going to use both of these as we work through. So if I take a to the power of 8 over 3, it could be written as a to the power of a third to the power of 8, which is Law 3. Or alternatively, it could be written as a to the power of 8 to the power of a third. So let's take a to the power of 8 to the power of a third. So breaking that down, I can take that power of a third using Law 6 and simply apply the cubed root to it. Or, working the other way, I can say let's take a to the power of a third to the power of 8, which then breaks it down to the cubed root of a to the power of 8. So we can see how both of these versions we can get to by using Law 6, and it just depends which we do first. And like I said, order does not matter. So therefore, a to the power of 8 over 3 is equal to either the cubed root of a to the power of 8 or the cubed root of a all to the power of 8. So let's take a look at Law 8 now. Law 8 says ab to the power of p is equal to a to the power of p and b to the power of p. So this is where we have a bracket, and it's important that when we have a power on a bracket that everything in the bracket is affected. So let's go back to looking at examples for this. Let's take AB to the power of 4. So that is AB by AB by AB by AB. And it's important to remember that AB itself is actually A by B. So we can split this into dealing with the A's separately and the B's separately, which splits it into A by A by A by A multiplied by B by B by B by B. So simplifying that up, we get A to the power of 4 times B to the power of 4. And remember, we don't need to do anything to show our multiplication in this case. Our final law is Law 9. And Law 9 is an extension of Law 8. Law 8 was a bracket to a power, and it said that everything in the bracket had to be affected by that power. Law 9 is an extension where in the bracket we have a fraction. So A over B all to the power of P is equal to A to the power of P over B to the power of P. So let's take A over B to the power of 4. So showing this as the fraction multiplied by itself 4 times, we get A over B times A over B times A over B times A over B. Remember, to multiply our fractions, we multiply across the top and across the bottom. So we get A by A by A by A all over B by B by B by B, which gives us A to the power of 4 over B to the power of 4. So let's get into some examples of using the laws of indices which we just worked with. So write A to the power of 3 times A to the power of minus 1 all over A to the power of 5 in the form 1 over A to the power of n, where n is a natural number, and that means it's going to be a positive whole number. So what I'm going to do is I'm going to try work with our laws as we go. So using law 1, I'm going to say A to the power of 3 multiplied by A to the power of minus 1 is A to the power of 3 plus minus 1. And that's still all over A to the power of 5. So cleaning that up, it's A to the power of 3 minus 1, which is A to the power of 2 over A to the power of 5. Now what I'm going to do, I'm going to use law 2. And law 2 states that if I have two numbers which I'm dividing and they are the same base or that same big number, we can subtract the power. So I get 2 minus 5. That gives us A to the power of minus 3. So we now have A to the power of minus 3, and in this case we're going to use, it is law 5. And law 5 states that if we have a to a negative power, we can do 1 over a and the power then becomes positive. And we have worked it through. So we now have it in the form of 1 over a to the power of n, where n is a natural number, and in our case n is 3. So let's take a look at a second example. Show that a times root a all to the power of 3 over a to the power of 4 simplifies down to root a. Again, I'm going to tell you as we use any of our rules. So the first thing I'm going to do is I'm going to get rid of that square root, and that's going to be using law 6. So that gives me a times a to the power of a half to the power of 3 all over a to the power of 4. So just remember in questions like this, because we're dealing with the rules of indices, it shouldn't make much of a difference which one you do first. In some cases it will, but they'll be very rare. So what I'm going to do next, you might work this slightly differently, but you will get the exact same answer. I'm going to use law 1 to clean up what's inside the bracket. And just to help us, a is actually a to the power of 1. So we get a to the power of 1 plus a half to the power of 3 all over a to the power of 4. Cleaning that up, I get a to the power of 3 over 2. And I would suggest in all cases to work with top-heavy fractions as much as possible. So the next thing I'm going to do is I'm going to clean up this top line, and in order to clean up this top line, we're going to work with law 3. So law 3 states a to a power to another power, we multiply our powers. So we get a to the power of 3 over 2 times 3 all over a to the power of 4. Let's clean this up. We get a to the power of 9 over 2. Remember, keep it top heavy. A to the power of 4. The last law that I'm going to use is law 2, and that means to divide our two numbers, we're going to subtract our powers. So a to the power of 9 over 2 minus 4. Cleaning that up, we get a to the power of a half, and the last change, we have it back to the answer we want, but we're going to work through, and we're going to say, using law 6, that we can change this back to being the square root of a, which is what we've been asked to get. So now let's take an example which looks a bit more complex, and the reason this looks a bit more complex is to use the multiplication symbol. So the first thing I would suggest to do in this case is to actually get rid of that multiplication symbol, because we're dealing with x's, it can get very confusing, and instead replace them with brackets. So always the first thing that I would do if I was looking at a question like that is to change any square roots that we have. And so we're using law 6 to do that, and we change any square roots or other roots that we have. In this case, we have a cubed root, so the x to the power of a 3 stays. This becomes x to the power of a third. That's all over x to the power of 2 times x to the power of 4. Now, both the top and the bottom line can be worked using law 1, which is when I'm multiplying, I add the powers. So I get x to the power of 3 plus a third all over x to the power of 2 plus 4. Simplifying this out, I get x to the power of 10 over 3. Remember, keep these as top-heavy fractions, over x to the power of 6. The next thing I'm going to work with is law 2, where I subtract my powers. So I get x to the power of 10 over 3, subtract 6. Let's clean that up. So I get x to the power of minus 8 over 3. So I am working these in my head, but you work your calculator, 10 over 3 minus 6, or if you would like to put that and do that separately, you can work it through with common denominators. So what I would say at this point is you've worked very well to get to this point. We have it broken down, but it is important to note that this answer is not in the form that we would generally want to see an answer. So we tend to stay away from two things in our answer. We tend to want to stay away from fractions and negative indices. So what we're going to do is we're going to change both of them. So although yes, we were at our final answer, we're going to manipulate it slightly. So I'm going to use law 5. And remember, law 5 was about the negative powers, and they said if I have a negative power, it becomes 1 over x to the positive power, which becomes 8 over 3. So the next thing I want to do is deal with that fraction. So if we take a look at our rules here, we're going to deal with law 7. And law 7 on that bottom line will get us to the cubed root of x to the power of 8, or it can be the cubed root of x all to the power of 8. And that form there would get you, as we move into leaving cert, it will get you your full marks as opposed to x to the power of minus 8 over 3. What I'd say is that in an exam question, you'll find that they'll be very specific about the format that they want your answer in. but it's a good idea that as you're working through questions in your book or where it may not be clear, that you should always get rid of the two things that we mentioned, which were negative powers and fractions in your power. So now we're going to look at some index equations. So when we have an indice, we have it attached to what's called our base. So that's our big number. We talked that through a little bit as we work through our laws, but it's important to remember that term, that the big number is our base, because as we move into the Leaving Cert higher level course, we're going to work with something called logs, and we're going to refer to this base again. So it's really important that you know where it is and you know the correct terminology to use. So we're going to solve some index equations, and index equations are equations where the variable or our letter appears in the power or the index. So if you think about a quadratic, we have an x squared plus an x plus a number. In that case, the x's are the bases, they are the big numbers. In this example we have here, we have 2 to the power of 3x is equal to 32 to the power of 3 over 5. So that x is in the power. So our way of working through this is going to be to get the base numbers on both sides to be the same. So usually it is straightforward for you to see what the base number should be. In this case, we're going to focus on this and see that the number should be 2, because there's nothing I can do with 2. It cannot be broken down anymore. So 2 to the power of 3x is equal to. So now I'm going to see, can I write 32 as 2 to a power? So all we can do in this case is trial and error. So you might be aware that 2 to the power, well, you should be aware that 2 to the power of 1 is 2 and 2 to the power of 2 is 4. You may also be aware that 2 to the power of 3 is 8. So it's definitely not 2 to the power of 3. So you can try 2 to the power of 4 and you get 16, which is not correct. And then you say 2 to the power of 5 and you get 32. So using trial and error, we can rewrite 32 as 2 to the power of 5. And this is all to the power of 3 over 5. So I'm going to clean this up, and to clean this part, the right hand side up, I'm going to use law 3. So left hand side, nothing can happen. And this becomes 2 to the power of 5 times 3 over 5, which simplifies down as 2 to the power of 3. 2 to the power of 3x. Now, let's take this part here. So I have 2 to the power of 3x and a 2 to the power of 3. Since I've broken this down into having the same base on both sides, what I can do is I can ignore the base. Because if the base numbers are the same, I can then say that the indices must be the same. Therefore, 3x must equal 3. So I'm looking at this power here must equal this power here, and simplifying that down by dividing both sides by 3, I get x is equal to 1. So let's take another index equation question and work through it. So again, remember, what we're trying to do in all these index equation questions is get both sides to be the same base. So I have 5 to the power of 2x minus 1 is equal to 1. Again, my focus is going to be getting both sides to be a 5 to a power. Don't forget your laws of indices. Law 4 tells me that any number to the power of 0 is 1. So I can say 4 to the power of 2x minus 1 is the same as 5 to the power of 0. I am able to rewrite that right hand side as 5 to a power. So sometimes people try to rewrite 5 as 1 to a power, but remember, 1 is a special type of number that no matter what power you put it to, it's still going to be 1. Because if you say 1 by 1, it's 1. 1 by 1 by 1, it's still 1. Keep multiplying 1 by itself and it's still going to be 1. So just be really careful. At this point, I ignore the bases and I focus instead on my powers. So in this case, I say therefore 2x minus 1 equals 0. So 2x is equal to 1. I'm adding a 1 to both sides. Divide both sides by 2 and I get x equals a half. So our final equation here, find the value of x for which 2 to the power of 2x plus 1 is equal to 8 to the power of x over 4. So there's a bit more going on in this equation because we have three different base or big numbers here. And again, we want to focus on what are we going to get them to. And the answer is 2. We want to rewrite everything as a 2. So I get 2 to the power of 2x plus 1 is equal to. Now, 8 can be written as 2 to the power of 3, and it's still to the power of x. And 4 can be written as 2 to the power of 2. So the next thing I'm going to do is for this top part here, I'm going to work with equation 3, just that top line. So the left hand side stays 2x plus 1. Law 3 tells me if I have two powers, I multiply it. So I have 3 by x, I have 2 to the power of 3x, all over 2 to the power of 2. I'm now going to use law 2, which says if I'm dividing two numbers, I subtract my powers. So I have 2x plus 1 is equal to 2 to the power of 3x minus 2. Now, I focus on my powers and I ignore my bases. So I ignore the base and I just focus on the power on each side. So therefore, 2x plus 1 equals 3x minus 2. First thing I'm going to do, I'm going to subtract a 1 from both sides. I get 3x minus 2 minus 1. Now I'm going to subtract a 3x from both sides. So 2x minus 3x is equal to minus 3. So I get minus 1x is equal to minus 3. Divide both sides by minus 1 and I get x equals 3.